In this video, we're going to start talking about a problem called the area problem, and we're just going to do a basic overview of this area problem today. So what is the area problem? Well, the area problem is a problem that really stumped mathematicians for quite some time until these methods were developed for how to solve it, and we'll be learning these methods in this video and in future videos, and eventually learning something called integration, which is the next big topic in calculus. So the area problem says, if I have a function and it is continuous and non-negative on some interval a, b, then what is the area of the region that I'm going to call R under the curve f of x and above the x-axis on the interval AB. So this area problem, we're asking, how do I find the area of a very irregular shape? If we have a very nice shape like a rectangle or a square or a triangle, all of the shapes we learned about in geometry class, we can find the area pretty easily using some formulas. But what if I just am looking at some weird shape that I get from looking underneath the graph of a function? How would I find the area of this weird shape? So let me draw a picture talking about the type of shapes we're talking about. So here's my interval a to b, and I just have a continuous non-negative function. We'll say there's f of x, and I'm asking, how do we find the area of that strange shape underneath the graph of the function and above the x-axis? That's not a nice shape like a rectangle or anything, so it can be pretty difficult to do. But actually, our first method for finding the area under the curve uses nice shapes like rectangles to help us approximate this area. And this first method is going to be called the rectangle method. So the rectangle method says that we should take our interval AB and divide it into n equal subintervals. And construct a rectangle of height f of some number xi for each subinterval. Then the total area of the rectangles is an approximation of the area of our region R. And in fact, the more rectangles we use, the better this approximation ends up being. So good, in fact, that we end up actually writing that the area is equal to the limit of the sum of all these rectangles as the number of rectangles goes to infinity. We're going to get into that a little more in a future section when we get a little bit more technical. But in this section today, we're just going to be talking about for a certain number of rectangles, estimating the area. So what I mean when I'm talking about making all of these rectangles to approximate the area, let me just draw a generic picture to help us to get the idea of the rectangle method. So again, if I have some function, and I'm talking about finding the area beneath that function and above the x-axis, so that's the area I'm trying to find. We're saying divide this interval AB into n subintervals, and I'm going to use n equals 4 just to illustrate this example. So if I divide my interval into 4 pieces, and then I construct a rectangle for each of these pieces that has height equal to some value on the function, then I have those 4 rectangles that I can add up and estimate the area. So I happen to draw my 4 rectangles here using the right endpoint of all the subintervals, but there's nothing stopping me from choosing to use the left endpoint or the midpoint or really any point that I want. When I chose the right endpoints here, you can see that some of these rectangles overestimate the area, like this first and this last rectangle stick out above the graph of the function. And the 2 rectangles in the middle are underestimating our area. And we can see this might actually not be that good of an estimation. But if you picture making more and more rectangles, skinnier and skinnier rectangles, we won't be as far away from this curve and we'll get a better approximation of the area. So let's do a very explicit example of how you would use this rectangle method. We're going to use the rectangle method with n equals 4 rectangles. To estimate the area beneath the function x squared on the interval 0 to 1. So I'm going to have 4 different rectangles that I'm using, filling up my interval 0 to 1, and we're using just the basic parabola graph to figure out how this rectangle method works. So first thing I should do is figure out how wide all of these rectangles are. I'm doing 4 rectangles, all of equal width, to divide my interval that is width 1 right now. So that means that my rectangles will have width 1/4. And I get that by taking the length of my interval, which is 1 minus 0, and dividing by the number of rectangles, which is 4. So all my rectangles are going to have a width 1/4, and their heights, well, it depends on what point I use in each subinterval, but it's going to be my function f with some point plugged into it for all of my subintervals. Let's draw a picture. So here's 1, 1. We know the graph of x squared is a parabola. Here's 0. And I'm using 4 rectangles to approximate this area. And my area is just between 0 and 1. So it's this sort of triangular shape, but it's curved there. So I can't just do the area of the triangle to estimate this. Let's divide this into 4 rectangles. I have 1/4, 1/2, and 3/4 as those division points. And I'm just going to go ahead and use the right endpoint just because. So I'm going to choose the right endpoint to make my rectangles. On this particular problem, this means I'm definitely going to have an overestimate because I can see all 4 of my rectangles are above the graph of the function, but that's okay. So I have rectangles of width 1/4, and I have to figure out the total area. Well, my total area I get by adding up the area of the 4 rectangles. And the area of a rectangle is just, length times width, or in this case, width times height. But that's how we would get the area of these rectangles. To get the height, we need f of these right endpoints. That's where I drew to make the top of my rectangle. So I would have f of 1/4 for the height times 1/4 for the width plus f of 1/2 for a height times 1/4 for a width, f of 3/4 times 1/4, and f of 1 times 1/4. So that's the area of my 4 rectangles all added up together. And this is equal to, well, my function's x squared, so I'm going to have a 1/4 squared times 1/4 plus 1/2 squared times 1/4 plus a 3/4 squared times 1/4 and plus a 1 squared times 1/4. And if I add all of that up, get a common denominator and everything, we're going to get that this is 15/32. Which, if I put that in decimal form, is 0.46875. Which, honestly, is not that good of an approximation. We're going to learn how to get the exact area a little bit later, but just so you know, the exact area is 1/3, which is 0.333 repeating. So, not the greatest estimate in the world there, but if we had taken more rectangles, our estimate would have been better. Now, of course, finding the area beneath a curve using all these rectangle approximations is not always the most convenient thing in the world. This can be very complicated to actually figure out the area. Let's do another example. Let's find the area between the graph f of x equals 2x plus 3 and the x-axis on the interval -1 to x, where x is just some number, it's a generic number. Then find the derivative a prime of x of the area function. So it's probably not clear right now why I'm bringing the derivative into this, but hopefully after we get to that point, you'll see why I'm bringing that up. So to find the area between that graph and the x-axis, I would suggest we first graph what this looks like. F of x equals 2x plus 3 is just a nice linear function, so we get a straight line. So I have the graph. Here's my plus 3, and my slope was 2. So I get, this is the graph of my function. Here's where -1 is, and I'm just going to put x here generically for now. We're talking about finding that area there. Well, the good news about this area is it's an area of a nice geometric shape. It's an area of a trapezoid. And the area of a trapezoid is given by 1/2 base 1 plus base 2 times h. where base 1 and base 2 are the parallel sides of the trapezoid, and h is the height of the trapezoid. So on this particular drawing, my base 1 and my base 2 are these vertical sides here. So this first side is 1. So I'm going just from 0 to 1. And the second side here, well, it's a little more difficult because I have just the x here, not a specific x value to plug in. But I know for whatever x this is, this height here is going to be 2x plus 3. So I'm going all the way up to my function. So my other base is 2x plus 3. Now the height of this trapezoid is this distance here between my -1 and my x. Well, that's a distance of 1 to get from -1 to 0, and then the distance of x to get up to x. So I have a distance of x plus 1. This is my area function, just using basic geometry. Now, if I actually distribute all of that, I will get that a of x is equal to x squared plus 3x plus 2. So there's the area of this region for just any x value. I could take an x value and plug it in and get the area of that particular trapezoid shape. The other part of this problem asked us to find the derivative of our area function. When I take the derivative of the function I got, I get 2x plus 3, which should sound very familiar because that's the function that I'm finding the area underneath. This was my original f of x. Is that a coincidence? Absolutely not. What this is telling us is the function representing the area underneath the curve of a function is going to be some sort of function that when I take the derivative of it, I get my original function again. So now the question is, if I hand you a function, how do I find the opposite of the derivative? And that's actually called the antiderivative. So I'm just going to put a note here. The derivative of our area function was the function f. The process of finding a function from its derivative is called antidifferentiation. And for what we're talking about right now, our area function is the antiderivative of the function that we're trying to find the area beneath. Well, that's kind of interesting. So let's do an example again. We're actually going to use that same example that we did earlier, the parabola on 0 to 1. But we're going to use antiderivatives to find the area. So we're going to use antidifferentiation to find the area under f of x equals x squared on the interval 0 to 1. Well, what do we know? We know that the area function is going to be equal to the antiderivative of f of x on the interval 0 to some x, where x is in the interval 0 to 1. So I need to find an antiderivative of my function f of x, and then I'm going to have to plug a 1 into that result to figure out the area from 0 to 1. Well, okay, let's try to find an antiderivative. What I'm trying to find is if f of x is x squared, I want a function that when I take the derivative of it, my answer will be x squared. So we have to think of our derivative rules, but do them all backwards somehow. We know when taking the derivative, the power ends up going down by 1 using the power rule. So if I'm going to get an x squared as a result, my antiderivative should have an x to the third, a power that's 1 higher. So what I know so far is I'm going to have an x to the third, but there's more to it than that. Let's think for a second. If I had x to the third as my antiderivative, what's the derivative of x to the third? 3x squared. But I only want it to be x squared. How do I fix that? I divide by 3. So now I have an antiderivative of 1 over 3 times x to the third. Let's check that. What happens when I take the derivative of this guy? Well, 3 would come down and multiply, canceling out the 1/3, and so I would just get x squared. Everything looks good, right? Well, not quite right. Because what if I have a 2 here? Is the derivative of that guy still x squared? Yeah, it is, because the derivative of 2 is 0. And then what's stopping me from making this a 27? Absolutely nothing. Derivative of 27 is also 0. So how can I write this generically? The antiderivative of x squared is going to be 1/3 x to the third plus c, some constant. Because no matter what constant I have added on there, when I take the derivative, that constant's going to disappear. So I don't know which exact antiderivative I need for this problem. I know it's going to be a 1/3 x to the third, but maybe I have some number added on to give us our particular area. So now the question is, how in the world do I figure out what that constant is? Well, this a of x is the area on the interval 0 to x. Let's pick the easiest interval we can. What if x is 0? If x is 0, we have a of 0 equals 1/3 times 0 to the third plus c. So I get a of 0 equals c. So what are we talking about for a of 0? We're talking about if this were my function graphed here, my x squared from 0 to 1, we're talking about the area from 0 to 0, just that point. What do you think the area of a point is? Well, it makes sense to say that's 0. So since a of 0 is the area of a point, we have our particular constant for this problem is 0. So that means our area function is just going to be 1/3 x to the third. And now we're ready to find the area on the interval 0 to 1. The area under our function x squared on the interval 0, 1 is a of 1. So I just have to evaluate. A of 1 equals 1/3 times 1 to the third, which is 1/3, which if you remember back earlier in the video, I said that's what the actual area is. We just didn't know how to get it yet. So We now have two methods for finding the area underneath the curve. One is using rectangles, and it gets us an approximation. That one's kind of nice because it's easy to understand, but it doesn't give perfectly accurate answers. Our other method is nice because we get an accurate answer, but it's a little complicated if you don't quite know how to find an antiderivative. So we have two methods right now, and in the next few videos, we're going to develop our skills to get real good at finding antiderivatives, and that will be our method of choice once we learn all of our techniques for finding antiderivatives. So imagine all the derivatives we've done all semester, and now imagine doing them all backwards. That's what we're building up to in these next few sections, and I hope you stick with me. If you have questions on the basic area problem, please drop them down below, or you may ask me in office hours or through email if you're one of my current students, and I will see everybody next time.